video time. Now, I only have 15 minutes of memory left on the card to do this, so I'm going to try to solve this in 15 minutes. I thought it was very important that you guys get a look-see at how to solve a problem with a capacitor in a more complex circuit than just a resistor and a capacitor in series with a battery. So now, here's what happens, okay? Initially, and this is very similar to, this setup is very similar to number 54 in your book. I just used slightly different numbers. It makes it a little bit easier on me. Okay? So initially what's going to happen is, okay, this switch is open so no current can flow. This is initially uncharged. I've got a 15 kilo ohm resistor, a 10 kilo ohm resistor, a 50 volt power supply, battery. This is a 0.4 microfarad capacitor. So now, let's say, there's a bunch of things that I want to figure out about this first. I ask a whole bunch of different questions than what the book does. So now, this is initially uncharged, no current's flowing, okay? The switch is now closed. Okay? So now, what happens? Okay? Remember what I said. Initially, this acts as a wire, because there's no charge on it, there's nothing that's going to, so there's no potential difference across here. So this just acts as a wire. So initially, no current comes through here. All the current's going to come through this capacitor. Okay? Again, let me restate that. This acts as a wire. If this is just the wire, the current won't come through here. It'll only go through here. Okay? It's the equivalent of seeing this. Okay? If there's no resistor here, the current doesn't go through the current won't go through the one with the resistor, it'll go through the current without the resistor. Okay? So now what happens is, we say that the 15 kilo ohm has no initial current. So all the current has to go through here. So now, initially I have 50 volts and 10 kilo ohms. Okay? So the current is going to equal, in that entire loop, there's no voltage loss across the capacitor. The only voltage drop is across the resistor here. So I've got V over R, which is 50 volts over 10,000 ohms. Okay? And we get 5 milliamps. Okay? 5 times 10 minus 3 amps. So now this is across the 10 ohm, this will be 5 milliamps. Now, the current has no place else to go because it's not going through here, so this will also be 5 milliamps. Now, technically speaking, there is a very slight resistance in the wires, so this is not going to be perfect. There will be a very slight amount of current that goes through the resistor as well. Now, after a long period of time, okay, this becomes fully charged. Okay? This will not take any more voltage across it. Okay? Now, you have to be very careful. The voltage across this will not equal 50. It does not, and we'll see why in a second. Okay? After a long period of time, this acts as a brake. So instead of seeing the circuit before where, okay, it's like this. There is nothing there. Current can't flow. Okay? So we imagine that it's just not there anymore. So now I have a 15 kilo ohm resistor and a 10 kilo ohm resistor. Okay? In that case, I've got the current is equal to 50 volts over 25,000 ohms. And this would give me 2 milliamps. So the current through the capacitor is 0, the current through the 15 and the 10 are 2 milliamps. Okay? Now, before we said that this capacitor, when it was just in series with the resistor and here, that capacitor charges up to 50 volts. I shouldn't say charges up to 50 volts, but you get the point. It doesn't in this case. Okay? There's still current that's flowing through this circuit. After a long period of time, there's still 2 milliamps that are flowing through here. So now, if I did a loop, of this outer loop here, okay, I would have 50 volts minus the voltage across the capacitor minus the current through here times that I through the 10 times that 10 kilo ohm resistor times 10 to the 5th ohms. That all has to equal 0. So now, this is 2 milliamps. Okay? This is going to be your, so now 2 times 10 minus 3, 20. Okay? We're going to wind up with, so make sure that my calculations were correct. So now current 10 is 2 times 10 minus 3 would be 20 times. Okay, yes, gotta check something real quick. 50 over 10 kiloohms. 50 volts. 10,000. Okay, it's going to be. So now, this is going to be 50 volts, that's voltage across capacitor. I10 is 0.002, 10 kilo ohms, there it is. 10, that's 10 to the third, I'm sorry, times 10,000, so that's going to be 2. So this, sorry about that, guys, 10 to the fourth. Is equal to 0, so this will be 20. So the voltage across the capacitor is not 50, it's equal to 30 volts. Something very important to pay attention to. Okay, now, I didn't talk about discharging the capacitor. Okay? Let's think about what's going to happen now after a long period of time. This is the positive end of the capacitor now. It's going to act as the battery. Okay? It's going to flow through this resistor. So current is going to flow through this resistor in this direction. Okay? Now, okay, the switch now is opened after a long period of time of charging up. So this goes like that. Now, the current through the 10 kilo ohm resistor, it's never going to happen anymore. There's no more current through the 10 kilo ohm resistor. It's gone. The voltage of the capacitor here initially is still that 30 volts. Okay. Now, what's going to happen is, unlike the battery, which has a chemical reaction which can keep pumping the charges, this only has a certain amount of charge that will flow before it gets back to neutral. So now, after a long period of time, the current is 0. It all points along. Initially, okay, this is going to be 30 volts. I have to lose 30 volts across here. If I'm going to lose 30 volts across there, okay, if I lose 30 volts across here, the current through that 15 ohm resistor initially, 15 kilo ohm resistor initially, is going to be, okay, 30 volts. It has to be 30 volts for that as well. Divided by 15 kilo ohms, okay, and I'm going to wind up with 2 milliamps. So the current isn't going to change initially. And there's only one loop, so the current here also has to be 2 milliamps. Now, how does this change as a function of time? Okay, let's think about what this should look like. Okay, if I made a graph of the voltage or the charge for that matter. Let's just take a look at the charge as a function of time. In fact, let's do voltage because I've got the voltage here. Voltage as a function of time. If that charge drops off, it's going to go like that. Now, we know that Q is equal to C times V. So now, all I'm going to do if I graph the charge versus time, it's just going to be V would equal Q over C. So all I'm going to do is divide by C. I get the same thing. So both the charge and the voltage are going to drop off as functions of time. Okay? So I'm going to start off with some value that's going to drop off. This right here is going to be your I times R essentially. This is going to drop off. Okay. So now, this is a function that goes as e to the minus t. So it's going to drop off from some value. This is an e to the minus t graph. Okay? If I'm going to make it more general, a e to the negative t over rc. Now, set up the differential equation for what this looks like. You should definitely be able to set up this differential equation. Do it before I'm finished erasing here. Pause it and get what this looks like. You have this. You have the voltage across there, so that's going to be, you have V equals Q over C. So I've got Q over C minus IR is equal to 0. So now, okay. So now, if I do this, okay, multiply, rearrange again, I've got dq dt. Let me just rearrange it first. Let's just say I minus 1 over RC Q is equal to 0. This is called a first order linear homogeneous differential equation. That means absolutely nothing. We'll get 0 points on the unit test. dq dt minus 1 over RC times Q is 0. Okay? So now, as a function of time, this looks similar to the other one, but it's going to start off at some value, and it's going to drop off. Okay? It's going to start off at Q0, e to the negative t over RC. Okay? You should definitely be able to set up the differential equation. Solving it, I'm not so much worried about. Now, that Q0, okay, we could also say that that's equal to the voltage across it. CV e to the negative t over RC. Okay. If I divide both sides by C, I get the voltage. So the voltage is going to equal V0 e to the negative t over RC. Okay. So I might not have the initial charge, I might only have the initial potential. Okay. So now, if I want the current flowing through here, okay, I have just going through the loop here, that voltage across the capacitor minus current through the 15 ohm resistor times the resistance would have to equal 0. So I have, and we can set this up for I as well. Okay. Now, I want you guys to take a moment and try to see if you can solve for the current here. Remember, and there's a couple different ways you can do it. You can look at it like this. The current's the same all the way through. Let's see. So I could actually just take the derivative of that, which will give you negative V over R, e to the negative t over RC. However you want to do it. Or Q t. That negative just means that the current is flowing opposite the direction that the original was. Right? I'm going to stop there, and then you guys will take it over.